Hi, welcome to the third and final video for week 5. In this we're going to look at the applications of derivatives and integrals, mainly looking at sine and cos functions. So these would be the questions you would expect to see in the modelling exams. The first one's probably more of a knowledge and procedures one, but we're going to run through it anyway because it's a good example. We want to find the equation of the tangent to the curve y equals cos x at the point where x equals 2 pi over 3. Okay, so remember the tangent of a curve is what the actual derivative gives us. So our function is y equals cos x. The tangent at that any point on that graph can be given by the derivative, which is negative sine x. And we want to find out what is that tangent when x is 2 pi over 3. So we're going to sub 2 pi over 3 into our derivative. So we've got negative sine 2 pi over 3. So 2 pi over 3, if we go back and use our cast diagram, and where does 2 pi over 3 sit? It sits here in this quadrant. So negative sine 2 pi over 3, it's still the negative, the sign doesn't change because even though it's positive there, we've got a negative sign here. So negative sine pi over 3, and using exact values, we have the gradient, or the value at that point. So the gradient of the tangent at 2 pi over 3 is negative root 3 over 2. So we've got our gradient at that point, and now we can just use our gradient point method, which again is from grade 11, 10 as well, to work out what the equation for that line is. So we've got y minus y1 equals m, the gradient, brackets x minus x1. y1 and x1 is just points on the y equals cos x graph. So we have a point here, x1. We know that at 2 pi over 3, that's our x value. We can work out what the y value is. So when x equals 2 pi over 3, what's the y value? Now we'll go back to our original graph here, the y equals cos x. So cos 2 pi over 3, again using the cast diagram, that because it's in that second quadrant, it is only sign is positive, so the cos becomes negative cos pi over 3, which is negative a half. So we have a point, we've got the gradient is negative root 3 over 2, and we have a point on it on the original graph, y equals cos x, when x equals 2 pi over 3, y equals negative a half. So we've got our values here, we just substitute it into our equation. So y minus negative a half equals our gradient, negative root 3 over 2, brackets x minus 2 pi over 3. Simplify that down, and we can come out with our great equation of the tangent to the curve y equals cos x at that particular point. Okay, so just going through that motion, work out the gradient, find the derivative to work out the gradient. From that gradient we have a gradient, then have a gradient and a point, so we can use this form of the equation of a straight line to work out what the equation is. So a lot of our applications involving sine and cos come in the terms of simple harmonic motion. So all our vibration and waves are made up of repetitive movements back and forth through an equilibrium or central point, and this is simple harmonic motion. Okay, where the maximum displacement is equal to the maximum displacement on the other side. So in other words, our sine and our cos functions. So in this example, we've got a particle that moves in a straight line, so that its displacement from x, or displacement x from the equilibrium at point P at time t seconds, and we've got the equation here, x equals 2 sine 4t. So this is the displacement of our particle. We want to work out when does the first particle first return to an equilibrium point. Find the time at which the particle reaches its maximum displacement from p, so p is the original position. Find the expression for the velocity of the particle, and find the second time that the particle comes to rest after the initial time. So just on a graphics calculator or in a graphing software, let's have a look at what x equals 2 sine 4t looks like. So here you can see it starts at the equilibrium point, up to a maximum 2, down to -2, up, down, up. So it's just going to be continuing up. That's what our particle is doing. Okay, we have a maximum displacement of 2. You see it comes back to its original position a bit before 1. So these are around about that point. There's around about 0.8. Okay, so when we come to our question asking when does it return to its first equilibrium point, it should be around about 0.8, and we can just check that from the graph. So part A asks when does the particle first return to the equilibrium point. So when the particle's at the equilibrium point, displacement is 0. Okay, so we put 2 sine 4t, we make that equal to 0, because that's when its displacement is 0. When the displacement is 0, it's back at its equilibrium point. So 0 equals sine 4t, you divide both sides by 2, 0 divided by 2 is 0. So when does sine x equal 0? So from our understanding of what the sine curve does, we know that when x equals 0, pi, 2 pi, 3 pi, 4 pi, and so on, sine will equal 0. So 4t, in order for sine 4t to equal 0, 4t must equal 0, pi, 2 pi, 3 pi, 4 pi, and so on. Okay, so obviously initially it starts at rest. We're looking for when does it first return to equilibrium point, and that is when 4t equals pi. So we can solve for t now. T equals pi divided by 4. Now if we put that into our calculators, we get the answer of 0.785 seconds, which from our graph you knew it was going to be around about 0.8. Second part of the question was to find the time at which the particle reaches its maximum displacement. So again, the maximum displacement for this function, as we saw from our graph, was 2. Maximum value of sine 4t is 1. 2 times 1 is 2, so that's our maximum displacement. So maximum displacement occurs when x equals 2, so 2 equals 2 sine 4t. Divide both sides by 2, and we get 1 equals sine 4t. Now we also know we have a maximum displacement when sine x equals 1, and that occurs at pi over 2, 5 pi over 2, 9 pi over 2, and so on. So again, we just equate 4t, what's after that sine, with these values here. So the first time it reaches its maximum displacement is pi over 2, so 4t equals pi over 2. Solve for t, we get pi over 8. So the particle is first at its maximum displacement after pi over 8 seconds. And again, we could go back to our graph and verify that that was the case. Now we want to find an expression for the velocity of the particle. So if we remember back to our motion calculus, velocity is the derivative of the displacement. So we can work out the velocity by finding the derivative of our displacement. So all we're going to do is find the derivative of our expression 2 sine 4t, just using our derivative rules. Velocity equals 2 times 4 cos 2t. So that's just applying the derivative to that. So we get 8 cos 4t meters per second. That's our general expression for the velocity. When does it find the second time the particle comes to rest? So it starts at rest. Next time it comes to rest, particle comes to rest when the velocity is 0. So we set this velocity equation to equal 0. So if 0 equals 8 cos 4t, when does cos x equal 0? Or when does the cos function equal 0? It equals at pi over 2, 3 pi over 2, 5 pi over 2. So the second time it comes to rest is at 3 pi over 2. So we let that 4t equal 3 pi over 2 and solve for t, which gives us 3 pi over 8. So after 3 pi over 8 seconds, the particle comes to rest for a second time. So those are fairly common types of problems you can expect to see. We're going from displacement to velocity to acceleration, and using integrals we can go back the other way, which is what we're going to look at now. So here we've given the speed at the end of a vibrating spring is given by v equals 0.6 cos 3t meters per second. At time t equals 1, the spring has a length of 80 centimeters. Find an expression for the length of the spring and hence find its maximum length. So like I said, since the velocity is the derivative of displacement, displacement is the integral of velocity. So these things are just things you need to remember. So our velocity is 0.6 cos 3t, our displacement is going to be the integral of that. So again, just using the integral properties that we looked in the previous video, 0.6 can come out in front of the integral, and when we do the integral we have 1/3 sine 3t plus c. So our expression for the displacement is 1/5 sine 3t plus that constant c. Now we need to work out what that constant c is, and what we do know is that when t equals 1, the spring has a length of 80 centimeters. So we can use that, because we're in meters, we convert that to meters, 0.8. We can use those values to work out what our constant is. And just remember, make sure your calculator is in radians, because when we do derivatives, we're always using radians. So we can sub this into our equation, 0.8, which is our displacement, equals 1/5 sine 3 times 1 plus c, and then rearranging this equation and solving for c, we have c equals 0.8 minus 1/5 sine 3, which is 0.7718. So our general equation, or our equation for the displacement is 1/5 sine 3t plus 0.7718. So we've got our expression for the length. Now we want to work out what is that maximum length. So this is our displacement. We know that the maximum length occurs when this value sine 3t equals 1, because the maximum value of the sine ratio is 1. Therefore, what is the maximum length? For that to be a maximum, that's going to be 1. So you get 1/5 times 1 plus 0.7718. We just substitute that in, and we get 0.9718. So our maximum displacement of the spring is 0.9718 meters. So those are 3 fairly good examples, I think, of using integrals and derivatives of trig functions in applications and modeling environments. Just really need to remember displacement is velocity is the derivative of displacement, acceleration is the derivative of velocity, and velocity is the integral of acceleration, and displacement is the integral of velocity. And we'll spend a lot of time over the next few lessons, working through those modeling problems.